This is Lesson 12 in our Calculus 3 series, Limits. Let's start with limits of functions of two variables, and the notation looks like this. The limit of f as xy approaches ab is equal to L. The limit of f as xy approaches ab is L. And what do we mean by xy approaching ab? Remember that these are points in two-dimensional space. So as xy approaches AB, we're talking about from any direction. xy can approach AB along any path in the domain D of f. So let's take a look at that. If this pink region is our domain D and this is our point AB, talking about xy going to AB, xy could approach AB from any direction. It could approach this way, it could approach this way, it could approach this way. It could even do something crazy like spiral around and end up in on AB. So when we say the limit of f as xy approaches AB is equal to L, and that means along any path, it means that this needs to be the same limit along any path. With functions of one variable, we saw limit as x goes to a from the right of f of x must equal limit as x goes to a from the left of f of x. Those were the only two directions that existed. But now that we're talking about xy and ab in a two-dimensional region, there's infinitely many curves and directions along which xy could approach ab. And for this limit to exist, the limit needs to be the same along every path. So we definitely need a more formal definition of limit here so that we can prove limits exist and we can know for sure when we find them. And keep in mind that what we want this definition of limit to say is that we could get as close as we want to the limit L by finding some points close as we need to AB. So what would that look like in a formal definition? This is the epsilon delta definition of the limit. We say that the limit of f as xy goes to ab is equal to L if, for any epsilon greater than 0, there exists delta also greater than 0, such that if xy is in the domain, and if the distance between xy and ab is less than delta, then absolute value of f of xy minus L is less than epsilon. So what we're saying here is if for any epsilon greater than 0, we're saying as close as we want to get our function values to this limit L, we can find a closeness that we need between xy and ab. So that when xy is this close to ab, the function values will be this close to L. So again, if for any epsilon greater than 0, that's saying however close we want our function to be to that value of L, we can find a delta for which the distance between xy and ab is less than delta, guarantees that our function will be within epsilon distance of L. So we're saying that if we want to get our function values within epsilon distance of L, then we need to be able to find a circle of radius delta around point AB so that all the xy points in here get mapped into this interval. That would say that the limit as xy goes to AB of f of xy is equal to L. As close as we want to get to L, we can find a neighborhood around AB so that all those points get mapped into this interval. And let's take a look at this in 3 dimensions as well. If we want our function values within this interval, then that means there has to exist some neighborhood around this point for which all the function values lie within that interval. If we can do this for any value of epsilon, then we can get as close as we want to L, and we can say the limit as xy approaches AB of f is equal to L. Now let's take a look at some examples. For these, we want to find the limit or show that it does not exist. How can we show that this kind of limit does not exist? We said for the limit to exist, the limit needs to be the same from every pathway, right? From every curve going from xy to ab, it needs to be the same. So all we have to do to show that the limit does not exist is to find two paths along which the limits are different. And we're going to see a couple of examples of how we can do that. But if we can't show that it doesn't exist, we're going to need to show that it does exist and find that limit. So finding the limit means that we're going to guess the limit, then show that for any epsilon greater than 0, there exists delta greater than 0 such that the distance from xy to AB less than delta gives us f of xy minus L, an absolute value, less than epsilon. So it's going to be much easier to show that limits do not exist. But when they do exist, we are going to have to go through this definition or use a theorem that we see later on in the lesson. So let's take a look at some examples. The limit as xy goes to 0, 0 of x squared plus y squared over x squared plus 2y squared. Whenever you're doing a problem where you're trying to see if the limit exists, we said it's always going to be easier to show that it doesn't exist by finding a couple of paths along which the limits are different. Now here we're taking the limit as xy goes to 0, 0. So here is our point a comma b, right? That's 0, 0. And we want to know if this limit exists. So from every path that we can choose, will we get the same limit? We said it's going to be easier to show that there exist two paths for which the limit is different. Now where are we going to come up with these two paths? Well, the simplest way to get to the origin would be horizontally along the x-axis or vertically along the y-axis. So let's take a look at these two directions. If we take the limit along y equals 0, so that's the horizontal direction, then what we're looking at is the limit as x comma 0 goes to 0, 0 of x squared plus 0 squared over x squared plus 2 times 0 squared. Because we're looking at these function values, but we're only looking at the function values along this path. And along this path, all the y values are 0. So the function values that we're looking at are here. So this is essentially the limit as x goes to 0 of x squared over x squared, which is 1. Okay, let's take a look at the limit in the vertical direction. That's the limit as 0 comma y goes to 0, 0 of 0 squared plus y squared over 0 squared plus 2y squared. And that reduces to the limit as y goes to 0 of y squared over 2y squared, which is 1/2. So here we're saying we're taking the limit of the function values, but we're going along only these paths, which is where x is equal to 0. So the values that we're looking at, the function values we're looking at, have x equals 0 in them. And so it's this limit that we're computing, which comes out to be 1/2. And we can see that the limits are different in the horizontal and vertical directions. Therefore, this limit does not exist. So since the limits are different along x equals 0 and y equals 0, this limit does not exist. And sometimes we write that as DNE. And I want to point out, just to be clear, these could be any two curves that you find for which the limits are different. So it doesn't have to be these two paths. These are just a couple of easy ones to look at. So I want to say we found two paths along which the limits are not equal. Let's take a look at another example. So now we're looking at the limit as xy goes to 0, 0 of xy over x squared plus y squared. Notice again that we're going towards 0, 0. We're going to do this a lot just for simplicity, but note that limits exist towards any point. So let's take a look at this one, and let's start by looking for two curves, again, for which the limits are different. So we'll again start with the limit along y equals 0. So we have limit x0 goes to 0, 0 of x times 0 over x squared plus 0 squared. Now notice here, we're taking the limit as x approaches 0. So for all of these values, x is not equal to 0, and this becomes 0 over x squared. So this limit is in fact 0. We're not dividing by 0 here for sure. So this limit is equal to 0. Now what about the limit along x equals 0? We have the limit as 0y goes to 0, 0 of 0 times y over 0 squared plus y squared. Same thing is happening. We're taking y approaching 0, so y is not equal to 0 for any of these computations, and we get 0 over non-zero, and this is also equal to 0. Okay, well the limits are the same then, going in these two directions. Does that mean it's the same everywhere? No. It means that the two directions for which we looked at, they have the same limit. But for this particular limit, there is another direction in which the limit is different. Let's take a look at that. Let's take a look at the limit along y equals x. That's this direction here, along y equals x. If y is equal to x, then we're going to have limit, say, x goes to 0, 0 of x times x over x squared plus x squared. So we're going to have limit as x goes to 0 of x squared over 2x squared, and that is 1/2. Now we have a different limit, so this limit does not exist. Since the limit is different along y equals x and say y equals 0, this limit does not exist. Now let's take a look at another example. Limit as xy goes to 0, 0 of xy squared over x squared plus y to the 4th. So again, we're trying to see if this limit exists, and if it does, we want to find it. And to explore whether or not this limit exists, we want to find some limits along some easy curves. So we want to take a look at when y is equal to 0, when x is equal to 0, maybe y equals x, and perhaps some others to see if we can find two curves for which the limits are different. So let's start with the limit along y equals 0. We're going to have limit as x 0 approaches 0, 0 of x times 0 x squared plus 0 to the 4th. And again, as x is going towards 0, x is not equal to 0, so this division is 0 over non-zero, and this is equal to 0. Let's take a look at the limit along x equals 0. We have limit as 0y goes to 0, 0 of 0 times y squared over 0 squared plus y to the 4th. Again, as y approaches 0, y is not equal to 0, so we have 0 over non-zero, and this limit is equal to 0. Let's take a look at the limit along y equals x. So we have the limit as x comma x goes to 0, 0 of x times x squared over x squared plus x to the 4th. And this denominator is x squared times 1 plus x squared. So canceling an x squared, we get x over 1 plus x squared. X is going towards 0, and so this is going to give us, again, 0. Now we found three curves for which the limit is the same. Does that mean this limit exists and equals 0? No, unfortunately, it does not. Let's take a closer look at this function, and let's see if we can think of a path that might give us a different value. Notice in the last example, we had xy over x squared plus y squared. The roles of x and y were identical in this function. If we switched x and y, the function would be exactly the same. So going along y equals x is what gave us that different limit. But that's different than what's happening here. The roles of x and y here are not the same. We have an x and a y squared. We have an x squared and a y to the 4th. So if we want to get something similar to what happened here, where our denominator adds up and simplifies with our numerator, we're going to need x to equal y squared. If x equals y squared, then we're going to have y to the 4th plus y to the 4th in the denominator, and then we can do some simplifying. So let's take the limit along x equals y squared and see what that gives us. With x equal y squared, we're going to have y squared over y to the 4th plus y to the 4th. So that's limit as y goes to 0, y to the 4th over y to the 4th plus y to the 4th. and this is 2y to the fourth, so this is going to be 1/2. And that gives us our different limit, and now we know this limit does not exist. Now let's take a look at a limit that does exist. We have the limit as xy goes to 0, 0 of 2xy squared over x squared plus y squared. Now, if we took the limits as in the previous examples along y equals 0, x equals 0, y equal x, and any other curve we could think of, we're going to get the same limit each time. What is that limit going to be? We'll take a look at just one of these directions to compute that limit, and then I'm going to leave as an exercise for you to check the other curves, and we'll move on to show that the limit does exist. So the limit along, say, y equals 0, we have limit x 0 goes to 0, 0, 2x times 0 squared over x squared plus 0 squared. That is going to give us 0 over non-zero. That limit is equal to 0. And as an exercise, I want you to examine the limits along x equals 0 and say y equals x. You'll notice you'll get the same value of 0. But I'm going to move on now to show that this limit does exist and equals 0. To prove that the limit exists and equals 0, we need that for every epsilon greater than 0, there exists a delta greater than 0 such that the distance between xy and 0, 0 less than delta gives us the absolute value of f of xy minus 0 less than epsilon. Right? This is the epsilon definition of the limit. So we need to start with epsilon greater than 0 and show that we can find such a delta. And notice that we can simplify both of these inequalities. We need delta such that radical x squared plus y squared less than delta is going to give us f of xy, an absolute value, less than epsilon. What's f of xy? It's 2xy squared over x squared plus y squared. So we need to start with an epsilon greater than 0 and show that we can find a delta such that radical x squared plus y squared less than delta gives us a function value, an absolute value that is less than epsilon. So we say, let epsilon be greater than 0. And we're going to start with the left-hand side of this inequality, and we're going to do some math on it, and at the end we're going to end up with less than epsilon. So we'll start with 2xy squared over x squared plus y squared. Now, because we have a 2, a y squared, x squared plus y squared, that's all positive, this is the same as 2 absolute value of x, y squared over x squared plus y squared. Now, we know that y squared is less or equal to x squared plus y squared because x squared is greater than or equal to 0. That tells us that y squared over x squared plus y squared is less or equal to 1. So recognizing that this is less or equal to 1 gives us this quantity less or equal to 2 absolute value of x. We also know that absolute value of x is equal to radical x squared, and that must be less or equal to radical x squared plus y squared, since y squared is greater than or equal to 0. So this is now less or equal to 2 radical x squared plus y squared. Now remember where we're going with this. We want this to be less than epsilon. And in order to do that, we want to show that we can find a delta such that if radical x squared plus y squared is less than delta, then this is going to be less than epsilon. Well, if we let delta be epsilon over 2, then we know that this is going to be less than delta, which is epsilon over 2. And so we'll get from here less than 2 times epsilon over 2, which is equal to epsilon. So let's look at this from the top again. We want to start with epsilon greater than 0 and show that we can find a delta such that radical x squared plus y squared less than delta gives us this function value, an absolute value, less than epsilon. We start with epsilon greater than 0. We say take any epsilon greater than 0 As we get to this point in our computation, we realize that, oh, delta should be epsilon over 2. That would work out great. So we say let delta equal epsilon over 2. Then, if radical x squared plus y squared is less than delta, if this is less than epsilon over 2, we have the inequality we need. So for any epsilon greater than 0, we can take our delta to be epsilon over 2, and we get our function value as close as we want to the limit of 0. And we've proven that this limit exists and equals 0. Now, fortunately, this isn't the only way we can show that a limit exists. We can also use the Squeeze Theorem. Suppose that f of xy minus L in absolute value is less or equal to g of xy for all xy in some circle centered at AB except possibly at AB. If limit as xy goes to AB of g is equal to 0, then the limit as xy goes to AB of f is equal to L. So what does all of this mean? So we're trying to show that as xy goes to AB, f of xy goes to L. So we need to show that this difference in absolute value is going to 0. Well, if we know that this difference in absolute value is less than some other function value that goes to 0, it must also go to 0. It's less than something that is going to 0. It must also go to 0. And that's how the Squeeze theorem is used. But in order to use it, we need to have a good collection of functions g of xy for which we know the limits. And that's going to come once we talk about continuity in the next lesson. So we're going to end our lesson on limits here. And you'll see more about the Squeeze theorem in the next lesson.